Hello. Title for this lesson is Polymers. We're learning about polymers today. So as always, pop your date, title, keywords down and then the do now task. Sorry, I have spelt polymerization, or autocorrect has the American way. That's better. So today's lesson is on polymers, which are a group of materials. As always, they've got specific properties that help them do certain jobs for us. So pause the video while you get that down and do the do now task. I'm now going to go on to the answers to the do now task. So hopefully you remembered group 1 elements lose a negative electron and therefore they form a positive ion with a single positive charge. Oxygen is in group 6, so it gains 2 electrons, giving it a 2 minus or 2 negative charge. Magnesium group 2 loses 2 electrons, so has a charge of 2 plus. And iodine in group 7 gains an electron to form a negative ion with a single charge. Remember, atoms do this. They gain and lose electrons because they're trying to achieve a full outer shell. Okay, if you are in my lovely Year 11 class that have the misfortune of having 2 double lessons with me today, then I have taken pity on you and produced note sheets for you, so you can fill these in through the lesson rather than taking lots of notes. So if you haven't already got that, just pause the video now while that's being handed out. And also I want you to have this list of keywords. We're almost at the end of this section of our materials topic. And I want you please to take some time having a look through these keywords and definitions. These are keywords and definitions you are expected to know. So for now, just make sure you get a copy of those before the lesson continues, and you'll have a chance to look at those later on. So the video can be paused here, or I'm moving on to the next points. So what do we mean by polymers then? Well, polymers are really, really, really large molecules. So they're really, really large chains of small molecules joined together. So the diagram on the right shows that quite nicely. The small molecules are known as monomers, and they're all the same as each other. And through a chemical reaction known as polymerization, they are joined together in a repeating pattern to make what's called a polymer. And these polymers can be thousands and thousands of monomers long. Okay, so in a polymer, the monomers are all identical to each other. And then the polymer is made up of a repeating pattern of that monomer. So polymer A could be made up of monomer A repeatedly, polymer B made up of monomer B repeatedly, and so on. Okay, so we get lots of different polymers, but each polymer is made up of a single monomer joined together in a repeated pattern. So this might help you remember we've got lots of oligomers in polymers. So we name polymers based on the monomer that was joined together to make them. So you can work out what the monomer was from the name of the polymer. So polystyrene and polybutadiene and polycarbonate, these names tell us what the monomer was that was used to make the polymer. So the monomer used to make polystyrene is called styrene. So polystyrene is basically lots of styrene molecules joined together, hundreds and hundreds or maybe thousands of them joined together to make these really long polymer molecules. Polybutadiene, made from the monomer butadiene, and polycarbonate, made from the monomer carbonate. So poly means many. And so if we know the name of the monomer, we can have a fairly good stab at the name of the polymer. So for example, ethene goes through a polymerization reaction to make polyethene, which we shorten in everyday life to polythene. So polythene bags are made of the polymer polythene or polyethene, which is made from the monomer ethene. So take a second to just think through what the names of these polymers might be made from these monomers. So it's fairly straightforward, though, as I say, sometimes there's slight changes to the ends of the names. Propene makes polypropene or polypropylene. Tetrafluoroethane actually makes polytetrafluoroethylene. And chloroethene makes polychloroethene. So you can see there is a pattern, although sometimes the very end of the name changes. You would only ever be asked to interpret ones that follow a really straightforward pattern. Now, there are natural and synthetic polymers that we use in everyday life. Synthetic means man-made. Natural means found in nature or naturally occurring. So let's just go through and see if we can guess which are which. So Teflon. Teflon's used as a cable insulator in non-stick pans. You can jot these down as we go, and the video can be paused once they're all up so that you can just make sure you've got them all written down. So Teflon, silk, latex, polyester, wool, and nylon, all examples of polymers. So have a think about which category they would go into. Oh, sorry, I thought that was going to give you the answers. So latex is a naturally occurring synthetic polymer. Sorry, latex is a naturally occurring polymer. It's a type of rubber. Wool is also naturally occurring. It obviously comes from sheep. Silk is naturally occurring. It comes from worms, silkworms. The others are synthetic. So polyester, nylon, and Teflon, all synthetic. So the properties of polymers then: low density, so they're very light, they're flexible, they have low thermal conductivity, in other words, they're good insulators, and poor electrical conductivity, so good electrical insulators as well as good thermal insulators. And polymers can be either what we call linear or cross-linked. So let's start with linear. I think there's a section of this on that note sheet that you might have in front of you. So if we have a look at this diagram here, here's one line of a polymer molecule, a polymer chain. Here's another line showing another polymer chain. So in a linear polymer material, our molecules, our long polymer molecules, are laid out sort of parallel to each other. But there aren't any sort of strong bonds between these two long polymer molecules. And of course, this pattern would be repeated over and over again. There'd be hundreds or thousands of these. There are just these weak intermolecular forces. We've heard this term before, intermolecular forces or intermolecular bonding. These weak forces of attraction we've talked about in terms of graphite layers, and also the weak intermolecular forces between simple covalent molecules. So very similarly, these molecules are weakly attracted to each other, but there aren't any strong bonds holding them together. So that makes the material really, really flexible. You can stretch these materials, but they'll retain the bonds are strong enough that they'll retain their original shape, but do allow the materials to be stretched. Now, in cross-linked polymers, we've got, again, the polymer chains, but they are actually connected to the chains that are parallel to them by very, very strong covalent bonds. What effect do you think that would have on the properties of these? Well, if we've got really strong covalent bonds holding these links together, that means that there isn't really a potential for these polymer molecules to move alongside each other. So you really sort of strong plastics, like the plastics we make, like plastic classroom chairs and those sorts of things, or camping furniture, that really, really rigid plastic, lunch boxes and things like that, or storage containers, they're made from cross-linked polymers. So your linear polymers are things like plastic bags, where you've got sort of stretchy, flexible fabrics. Or maybe some of the polymers used in synthetic clothing, where you can stretch the clothing, but it returns to its original shape. Your cross-linked polymers are your rigid plastics. So the more cross-linking we have, the stronger the polymer material will be. So here's a diagram just showing you that. If you'd like to pause the video here, you could just make some notes from that slide. You could do a quick mind map of the main points around linear polymers. I'm going to move us on now to a similar slide on cross-linked. Again, you could pause that, make some notes on it, and then we're going to watch a video about different types of polymers. So I'm going to move on to the video now. So the video talks about thermosetting and thermosoftening polymers. Those aren't terms you need to know in any detail, but this video really nicely shows you some of the different properties in different polymers, and that's why I want to show it to you. So I'm going to move myself out of the way. In fact, I'm going to get rid of my face. Here we go.
The term polymer is used to describe a macromolecule made of many monomers or repeating units. The properties of these polymers all depend on a variety of factors: the monomer unit, the linkages between each monomer, and the intermolecular and intramolecular forces that exist between polymers. In this lesson, we will learn about two classes of polymers: thermosoftening polymers and thermosetting polymers. We will also learn about their properties and how these properties arise. The term plastics is used to describe a wide range of polymers made of monomers, all derived from the products obtained from the fractional distillation of crude oil. You may be familiar with polyethylene, polypropylene, and even polyvinyl chloride. You can learn about the structure of these polymers, how they are made, and their real-life applications from other videos on our channel. Here, we will focus on how these polymers respond to heat and why they respond the way they do. Polyethylene, polypropylene, and polyvinyl chloride are thermosoftening polymers. This means that they soften when heated. When soft and in liquid form, they can be molded into many different shapes. These plastics are used to make many everyday items, such as window and door frames, pipes, wiring insulation, and waterproof clothing items, just to name a few. This is made possible because polymers are not linked together. We can think of it like a bowl of noodles. Although the noodles are coiled and tangled with one another, they are not linked. Like the noodles, these polymers can slide over one another, making these items made from them soft and flexible. In fact, these polymers can only interact by weak intermolecular forces and can therefore be separated rather easily when heated, giving them relatively low melting points. Some other thermosoftening polymers include polystyrene and polytetrafluoroethylene. Thermosetting polymers, on the other hand, do not soften when heated. Unlike thermosoftening polymers, these thermosetting polymers are cross-linked to one another. Can you think about how this might affect the properties of these polymers? Pause, think, and continue when ready. The presence of cross-links hardens the overall structure. A good example of a thermosetting polymer is vulcanized rubber. Rubber tapped from para-rubber trees is a polymer of isoprene monomers. It is a runny liquid that can be processed to make latex gloves, erasers, and party balloons. It can also be used to make car and bicycle tires, though it has to be vulcanized first. For the vulcanization process, sulfur is added so the disulfide bridges link the polymers together. The presence of these cross-linkages greatly increases its strength and therefore does not soften easily when heated. Let's think about it. No matter how fast you ride your bike, the tires do not change shape. Some other examples of thermosetting polymers include a substance used to make old TV sets and certain types of strong glue. In summary, thermosoftening plastics are soft and melt when heated, whereas thermosetting plastics are hard and do not soften or change their shape when heated.
Okay, so as I say, thermosetting and thermosoftening. Thermosetting and thermosoftening are not things you need to remember in any great detail, but you do need to understand that it's the linear or cross-linking structure of the polymer molecules that gives those different properties. Also, I realised while I was watching that video, I made a mistake earlier when we were talking about natural and synthetic polymers. I said to you that latex was a naturally occurring substance. I was thinking about rubber. I'm sorry, rubber is naturally occurring. Latex is a synthetic product made out of rubber. So apologies for that. If you wrote that down wrong, you need to just correct that quickly. So rubber is a natural polymer, but latex is not. Okay, right, let's move on. So back to natural and synthetic polymers. So as I said, your natural ones are found in nature or come from living things, and our synthetic ones are made from petroleum or from oil originally. So pause the video and just make sure you've got a note somewhere on your sheet or on paper of those examples of natural and synthetic polymers. And moving on. Okay, a quick task for you. The table below shows you lots of information about a variety of polymers. Now, as you know, this topic is all about materials and their properties and how we design or select materials for certain jobs. So perhaps with the person next to you, pause the video, have a quick chat about which materials in the table you would choose for each of those 3 uses: drink for a hot cup, cup for a hot drink, a clothing, or a measuring cylinder, giving reasons why. And moving on to the answers. Okay, so A was a disposable cup, so we need a low cost material, and we need a high melting point because it's for hot drinks, so that would be Z. For our clothing, we'd choose material X because it's flexible and we can make it into fibres. And Y, it's transparent and resistant to chemicals. Obviously, if you're using a measuring cylinder in a lab, you're going to be measuring out volumes of acids and those sorts of things that needs to be resistant to chemicals, and you need to be able to see through it. Another example of polymers now, Kevlar. You might have heard of Kevlar in the context of bulletproof vests. Kevlar is not only used for bulletproof vests, but that is one of its most well-known uses. It's a synthetic, so man-made polymer, really, really strong bonds between the chains, so that it's really, really strong despite being low-density, lightweight material. It's also incredibly flexible, which means it's useful to be put into clothing. I'm going to show you a video now about some of the uses and properties of Kevlar. So this is a bulletproof shield. Just move that out of the way. A bulletproof shield that's been designed using Kevlar.
We're working on an origami-based, deployable ballistic barrier that will keep emergency personnel safe during a hostile situation.
We met with federal agents that often use current shields and asked what could help them to better do their job.
Current products out there are about 90 pounds. That's pretty heavy for one person to carry, and it only protects one person. Our goal was to go for 50 pounds and protect 2 to 3 people.
This pattern is the Yoshimura crease pattern, and when it deploys, it provides these nice angles, which we hope will be even more effective shape for a barrier. So going from paper to other materials can be really challenging.
It has 12 layers of Kevlar with an aluminum core in the middle. The students did a lot of calculations, and 12 layers is really what you need to be able to withstand a bullet from a handgun. One of the great things about this particular fold pattern is that it opens and closes really easily. In an emergency situation, you've got to be able to just get that thing open and get it in the way.
Today's objective was to see if it worked, if it actually stops bullets.
My first thought was, did he miss? So I went back to the high-speed camera that I'd been filming, and the bullet sunk right in.
Range is hot. It was exciting to see that it did stop the bullets, and we were able to successfully demonstrate it with 9mm, 357 Magnum, and 44 Magnum pistols.
The federal agents that saw our initial prototype were really excited about it.
Their response was that this is a revolutionary product.
My dad is actually a police officer himself. This could be something that could be used by him or other officers that could prevent injury or even save their lives.
So I think that's just fabulous. And I love the fact, not just the Kevlar that's used, but also just that origami design to unfold into a shield. It's such a simple development. Right. Sorry, I've shown you that already. These are the sorts of things that Kevlar is used for. So very, very strong, very, very light, but really a sort of heavy duty material in terms of its ability to withstand force and wear and tear. I've got another Kevlar vest video to show you. Sorry, I could have shown you that one just now. Let's go back to that. Okay, so as you can see, really, really versatile, important material. Okay, so thinking about other uses for Kevlar then. You can pause the video here if you want to and see if you can come up with some other uses yourself, but I'm going to go on and show you some other ways we use Kevlar. I don't need to read that out to you, you're perfectly capable of making sense of that. Okay, so to recap then, we've talked about polymers today, Kevlar being an example of that. Remember, polymers are made up of long polymer molecules, and a polymer itself, a polymer molecule, is made up of small molecules called monomers that are just joined together in repeating fashion over and over again. The properties, they're generally lightweight and strong. If they are linear polymers, they are very flexible. If they are cross-linked polymers, then they're more rigid and even stronger still, because those strong covalent bonds between the polymer molecules give them that strength. We've learnt about naming. The name of a polymer is usually poly followed by the name of the monomer or something very similar to that. We've learnt that there are natural and synthetic polymers around. So that's the last thing I wanted to go through on polymers. So if you've got some time left, spend a few minutes looking over the information, make sure you've got your head around the difference between the different types of polymers and their properties.